I'm just continuing the practice questions for grade 11 physics general. Let's see, we're doing some more energy questions. I had to stop the previous video because it was going to get too long. So what do we have here? Heat from a stove warming a pot of water. Heat is simply thermal energy. Thermal energy. Energy by electromagnetic waves such as light. So that's basically much radiation. Electromagnetic radiation. Light, X-rays, gamma rays, whatever it is, it's all radiation. So radiation, we call that radiant energy. Energy by moving electric charges. Well, there's a clue right there on the word electric. It was literally called electric energy. Electric energy, or electrical to be precise. In fuel, something that we have in fuels and it's going to get burned, that is normally chemicals energy. Chemicals get burned, so chemical energy. Chemical. Energy stored in the nucleus, there's a clue there. Nucleus means nuclear. Energy stored by plants in glucose, so energy stored in plants. Again, same idea as a fuel. Plants store energy to survive off, and that is simply chemical energy again. Food is also chemical energy. Chemical. Okay. Which of the following best describes the relationship between mass E equals mc squared? So E equals m squared, mass and energy are unrelated. Obviously that's wrong because it is related. There is an equals in between them. Inversely proportional? No. Inversely means divide. This means divide. I am not dividing. That would have meant E equals divided by m. So maybe c squared divided by m. This is an inverse relationship. That's wrong, obviously. It's not. It's multiplied. That's wrong. Directly proportional to mass? Well, yes, it is directly proportional to mass. As you can see, E equals mc squared. If the mass increases, this increases. This is directly proportional. And you can say directly proportional to the square of the speed of light. That's wrong. So this is the answer. Directly proportional to the square of the speed of light. You see that? That's c squared. This is mass. It's not mass squared. It is just mass. So directly proportional to mass. And what does it show us? So you convert mass into energy, and any amount of mass, and because it's multiplied by c squared, that's a big number, you know. C, the speed of light is 300 million meters per second. And then you're going to go and square that. Can you believe it? You're going to square that. Multiply that even by 0.01. You will get a huge number, a huge value for energy, whatever that number is. Okay, so definitely A is a good answer. They're not equal in magnitude because clearly it's going to be bigger because you're multiplying by c squared. Mass increases as energy increases. Well, the energy increases as mass increases, actually. That's a better answer. If there's more mass, you will get more energy as a result of that. And when you maybe reach grade 12, you'll be dealing with binding energy and stuff and the mass defect and things about the atom. So that'll be fun. Okay, the pendulum shows periodic motion. Very good. Maximum distance, the highest point, the maximum distance, we just simply call that the amplitude. That is called the amplitude. Amplitude. The period is literally the time it takes to go forward and back. If I started from here, how long it takes to go forward and back to where I started. The frequency is how many times it can do that in 1 second, for example. The speed is obviously how fast it's moving. So amplitude is the best answer over there. Continuing on to the next part, we're now looking at Hooke's law. So the extension 200, 2x, 100, x, 300, 3x, 400, 4x, but what is it saying? 50. Half of that. Half of 100, half of x will simply be x over 2. So it's directly proportional. F equals kx, technically negative kx. If I double my distance, or if I double my force, it will double the distance. If I half the force, I'll half the distance. So that's directly proportional. So if I said to you 300 grams, for example, 300 grams, that means it will simply be x, 2x, 3x. And you get the idea. Okay, very nice. All right, so let's move on to this one. And now we're going to do a bit of a calculation. F equals negative k. Oh, it's not a k, is it? F equals negative kx. We have my x. I don't have a force yet. That's a mass, but I can turn that into a force. That's easy. W equals mg. I will do 30.4 times 9.8. And that will give me my weight, which is a force. So I can quickly do that right now, actually. 30.4, that's not good at all. I must make that into kilograms. So 30.4 grams is times 10 to the minus 3, or just divide by 1,000, multiply by 9.8. That's more accurate. 30.4 times 10 to the minus 3, because I want to put it into kgs, multiply that by 9.8. My actual final force I'm going to use is 0.2979. 0.2979. I'm going to write that in here now. 0.2979, that's my force, newtons, equals to negative k, what I need to find, multiplied by x, 0.85. If you're very good at your math, it's obviously just divide, right? So I'm just going to go ahead and stick that in my calculator and just divide the two numbers. I'm going to use the answer, whatever the answer was. I'm going to divide that by 0.85. As you can see, it's magnitude only, so it doesn't really matter. I have 0.35. K 0.35. And it's supposed to be negative, but it's not important. Negative just means it's going in the opposite direction. If I go down, the force is pointing up. If I pull it up, the force is pointing down. That's the only reason we have a minus. So 0.35. A spring of constant here, 0.10, stretches to a new length of 0.15 when a block of weight is attached. What is the extension of the spring? So we need to find x, the extension of the spring. So as you can see, we have a relaxed one, and then we have a stretched one. The displacement, the extension, if you remember, delta x is what we call it, is final minus initial. So that's simply going to be 0.15 minus 0.10, which is 0.05 meters. Constant, F equals negative kx. And I want to find the constant, so I'm going to rearrange this time. K equals F over x. K is F over x. Let's go ahead and do it. F over x, what is the value for the F? That is 100. And the displacement was 0.05. Putting that into your calculator, hopefully, 2,000 newtons per meter. Newtons per meter. Newtons per meter. Okay, how much elastic potential energy does the spring have when it's stretched this far? You have two options. You can go ahead and do potential energy, so that is PE equals a half Fx, or you can do PE equals a half kx squared. You will get the exact same answer no matter which one you do. So let's just continue this one. Half times 2,000 times x 0.05 squared. Solving that, you should hopefully get 2.5 joules. That's not square, 2.5 joules. If you wanted to use a half fx, you can do. You could do a half times the force 100 times the displacement, which is 0.05. That's 50 times 0.05, which is about 2.5, which will get the same answer, 2.5 joules. Very good. So I prefer to pick the easy one, but you can choose any one you like. You get the same answer. How can you determine the following from a graph? So if you were having a graph, something like this, where did that line come from? And you had a graph. This slope of the graph, this is force, and this is going to be my, that's an F. This is my force, that is my displacement. Force divided by displacement, rise over run. Yes, y2 minus y1, x2 minus x1, rise over run from math. That's simply F over x. F over x, what's that? F over x, good thing I wrote it out. That's k. So that is my constant. So F over x, so how can you determine, is slope. That will be my k, my constant. I will write here, k. The energy is usually here, the area under the graph. Area under graph. Why, I hear you ask? I'll tell you why. Energy, or work done, is force times displacement. Or in this case, we have x. But this is a triangle. Force times displacement would be a square, F multiplied by x. But because this is a triangle, we have to have a half times the base times the height. We half it. That's where the formula comes from. Very nice. Okay, now we're moving on to some more Hooke's Law questions. Spring stuff. What are we doing? Contrast the potential energies of the bottom two springs. To contrast them. So all we're going to do is figure out these two here, here and here. Well, if I want to compare them, I can clearly see that this is further away, so this has more energy than the other one. And so I will say C has more potential energy than B. It might want you to know exactly how much more so you can compare the distances. So basically the idea here is all I need to really know is that what happens to my energy as I increase the distance. Let's find out. If I have this general formula, what's this called? PE equals a half kx squared. I'm using this formula. I'm using this formula because my force isn't changing. It's the same block of mass. So I'm going to use this one here. A half times k, which I can consider as 1, times 2 centimeters. I'll just keep it at 2. 2 squared. If I do that in my calculator, I'll get 0.5 times 1 times 2 squared. I will get, obviously, 2. Very nice. If I doubled it, I will do 1 over 2 times 1 times, that was 4 squared. What happens now? A half times 1 times 4 squared. That becomes 8. So the idea now is what I have just said. I have set this to 1 because it is the same spring. So I didn't need to care about the K. What I do know is that this will become 8 joules, for example, and this will be maybe 2 joules. 8 over 2 is 4. That tells me C is 4 times stronger than B. C has 4 times more potential energy than B. How did I do that? All I did was I used PE equals a half kx squared. I set K to 1 because it's constant. 2, I replaced 2 centimeters. It doesn't really matter if it's not converted. It's just keeping it simple. That will give me maybe 2 joules. I made this number up, but it actually ends up being 2. A half times, what did I do? I kept it as 1. A half times 1, because it's the same spring, times 4 squared. That became 8. To compare, that normally means to divide. 8 over 2, that becomes 4. It's 4 times bigger. You could, if you want to be awkward, you could say B is 4 times smaller. Yes, 4 times smaller than C. If you were to do 2 over 8, for example, you get 1 over 4. It's a quarter, basically, of C. Depends on which one you put up, which one you put down. Let's move on. Now we're looking at something here with the greatest potential energy. That is the maximum displacement. Maximum displacement you can see is right here. So I will say C. The greatest kinetic energy. Well, actually, I've noticed that this is equilibrium here. So not only C, A as well. C and A. Because this is maximum to the left, this is maximum to the right. Both are the same. So I will take that as the answer. Greatest kinetic energy means as it stops here, it stopped when it's maximum compression. When it stops, it then goes forward. As it goes forward, it passes equilibrium, but then it slows down when it reaches the maximum extension, then it stops. It goes back again, and it does the same repeating pattern. That's why it's called periodic motion. But each time it goes forward and back, the maximum speed ends up being at B. So that'll have the maximum kinetic energy there as well. Okay, now we're going to move over to the pendulum. Again, this video is getting a bit long, so maybe I will do the pendulum and then I will do waves in the next lesson, in the next video. So rank the following pendulums according to the period from the least to the greatest. Well, if you see length and the mass, actually, if you're looking at this, the mass, this is the formula here, T equals 2 pi root L over G. Why did I write it out? It's written right there. There is no mass in my formula, so I don't really care about the mass at all. I care about the length. I see the length. Now, if I see the length, this is directly proportional, so that means a longer length will have a longer period, because I'm not dividing by L. If I was dividing by L, I would be inversely, but this is directly proportional. So C has the greatest, so C has the greatest, so does D, so it's equal to D. They're greater than A and also greater than B. B and the A are equal, so equal to B. I've done greater than. It's asking for least, so all I do is I flip it. B and A is the same, so A and B, I'll write A first, alphabetical. A, B, less than C, which is equal to D. So I just flipped that. AB less than CD, AB less than CD, I pick C. Alright, determine the period of a pendulum, or does the period of the pendulum depend on the mass? I've already said that no, it does not. It is not in the formula. Didn't ask to explain why, so I'll just write no. Length, yes, because L is in the formula. It's literally in the formula. The amplitude, no, it does not depend on the amplitude. Technically it will if it's beyond like 12 or 15 degrees. When it reaches a certain length or certain amplitude, it kind of can. But in our curriculum, we're going to say no. What else does it depend on? Let's find out. What's the formula? 2 pi, that's a constant, L over G. G is what? G is gravity. Gravity. Very nice. What conditions are necessary for resonance? Resonance is when something is moving to the right, but then you also apply a force with your hand maybe in the same direction, at the same time, in the same phase. If you do that, you will match the natural frequency as moving forward and back. If I move forward and back at the exact same point, it will end up becoming resonant. It will start to get stronger and stronger and stronger. So it happens. So what can I say? It must not it. What can I say? The force must match the natural frequency. The force matches the natural frequency, and then it will continue. So this is moving back and forward. I move forward and back with it, and I can make it stronger and stronger. Because imagine, this was moving to the left, but then I put my hand in front of it and tried to push it to the right. I will slow it down. That's not what I want. If it's moving to the left already, and I grab my hand, that's not a hand anymore, and I also move my hand to the left, I am pulling it stronger. I am matching its frequency. And when it moves to the right, I go with the flow. So going with the flow is a good thing. And I'm going to stop there with this one. Thank you.